For decades, the automotive industry defined vehicle safety through a single lens: physical failure. Under the long-standing ISO 26262 standard, car crashes were understood as the result of a severed brake line, a short-circuited control unit, or a cracked sensor. If a piece of hardware broke, engineers analyzed the wreckage, found the snapped wire, and reinforced the design to ensure it survived the next million miles. Safety meant keeping the machine physically intact. Autonomous vehicles present a terrifying paradox. An AI-driven car can operate flawlessly, every wire connected, every software process executing perfectly, and still steer into a fatal collision. This happens because the physical world is chaotic. A camera lens catching the exact angle of sunset glare, while a pedestrian steps off a curb wearing a raincoat that perfectly matches the wet asphalt, creates a sensory gap. The sensors reach their performance limits, even when operating exactly as designed. To manage this reality, engineers adopted a strict new standard called SOTIF, or Safety of the Intended Functionality. Instead of hunting for broken components, SOTIF assumes the hardware works perfectly and focuses entirely on the system's functional insufficiency when it encounters confusing, real-world trigger conditions. The modern threat on the road is no longer a malfunctioning machine. It is a machine executing its programming flawlessly in a situation it completely misinterprets. This is the SOTIF safety matrix. It maps out everything a self-driving car will ever encounter by asking two distinct questions. First, is the situation safe or unsafe? And second, do human engineers actually know about it? Area 1 contains the known safe scenarios: clear lanes, sunny weather, standard cruising. Area 2 holds the known risks. If testing shows the car's cameras struggle to detect pedestrians crossing unlit rural roads at night, engineers document it as an Area 2 limit and program specific mitigations, like lowering the speed limit in those exact conditions. The true danger lies in Area 3, the unknown, unsafe scenarios. These are the risks engineers are completely blind to. They haven't programmed a defense because the specific sequence of events hasn't occurred yet. An open-world environment contains infinite variables. Developers cannot sit in a lab and imagine every bizarre weather phenomenon intersecting with obscure road geometries and erratic human behaviors. Engineering a safe autonomous vehicle requires solving an epistemological problem. You cannot write a line of code to protect against a risk you don't even know exists. This creates a very specific challenge. How do you systematically expose a fatal flaw hidden deep inside a system you built? You force the system into chaos. Engineers blast the vehicle software with massive randomized parameter mixing. They take variables like severe sun glare, wet roads, and abnormal pedestrian speeds, and scramble them together to see if they can trigger a failure. The data points on this scatter plot represent test variables shifting in real time using search-based software testing. Instead of guessing, an algorithm intentionally hunts for the exact combination of weather, speed, and angle that pushes the system over the red collision threshold. When the system finally breaks, that unique combination of variables is dragged into the light. What was an invisible threat in Area 3 becomes a documented risk in Area 2. Now, engineers can fix it. Safety testing under the SOTIF framework abandons the passive checklist of requirements. It relies on a hostile, automated hunt designed specifically to exploit the vehicle's ignorance. Executing this hunt requires a layered pipeline. It begins in the cloud with software-in-the-loop testing. Massive server farms run millions of these simulated scenarios, cycling through extreme environmental variations at speeds impossible to replicate on physical asphalt. Software simulation has a ceiling. It is only as accurate as the math behind it. To find the physical limits, developers move to hardware-in-the-loop testing. The actual electronic control units from the car are wired into the simulation, stressing the processors to uncover hidden memory limits and data bottlenecks. The final layer is real-world driving. This physical testing grounds the simulation data and acts as the only way to uncover the true unknowns, the deeply illogical, bizarre human behaviors that a perfectly logical computer model could never invent. Each stage of this testing funnel catches the specific blind spots left behind by the layer before it, filtering millions of virtual miles down to proven physical capability. Despite running millions of virtual miles and physical tests, this campaign against ignorance can never be perfectly won. The open world offers a mathematically infinite set of variables. Eliminating absolutely all risk or predicting every conceivable intersection of physics and human error is impossible. This returning SOTIF matrix shows the true objective, not flawless perfection, but systematic compression. Over continuous testing loops, the massive void of Area 3 is crushed down into an infinitesimally small sliver, while known areas expand to dominate. Engineers measure this compression against strict quantitative thresholds. Before a vehicle is deployed, they must mathematically demonstrate that its residual risk is lower than the natural accident rate of a skilled human driver. We cannot map every variable in the universe, but we can rigorously prove that the tiny sliver of the unknown remaining presents absolutely no unreasonable risk to human life.